We'll go on now to our last speaker, who's going to take the perspective of somebody who knows a lot about the grid and how these devices have to compete with other approaches. It's Dharik who's one of my close colleagues at the MIT Energy Initiative, who's a very talented young person. He's been working on an extensive number of models that look at these systems in great detail and try to answer big questions. So I'm looking forward to hearing from you. Dharik.
Rob, thank you very much. Let me just get the mechanics of this set up. Well, hello everyone. It's a great pleasure to participate in this panel. So, as you've heard from the previous two speakers, energy storage comes in a wide variety of forms and is a fairly complex technology, both to design, but then it's also made more complex when you think about sort of the applications we're thinking about in the future grid. And so, in this presentation, I'm going to take the view from the system perspective, particularly from the power system perspective, and to try to share with you what we're learning through some of our system modeling work with regard to what role storage might play in a deeply decarbonized power system. So just as some context, you've heard a lot about the different types of energy storage technologies, but I wanted to just provide some context about where energy storage has been playing a role in the electricity system to date. So if you just look back a few years, as of 2016, if you just focus on the battery storage market in the US, and I'm excluding pumped hydro from this chart, primarily all of the battery storage market was operating in the what I would call the high power, low energy applications around frequency regulation to manage imbalances between load and supply at short durations. However, this picture has largely changed in a very short span of time, partly driven by cost declines for lithium-ion battery storage, as you've heard from the previous two speakers. And here is just an example of a few project announcements made in 2019 talking about very large megawatt scale, multi-hundreds of megawatt scale battery deployments, often in conjunction with renewables across the US. And this is just a selection. There are many, many more announcements coming down the pike. So, clearly there is a shift here where energy storage has always been recognized to be able to provide a wide variety of grid services. Pumped hydro has been operating and is continuing to provide many of those services. But as battery storage has emerged onto the scene, it has originally started in the shorter energy application, but we're now starting to see it emerge into the more energy-oriented applications. And so this raises some interesting questions about what the role of pumped hydro storage is going to be and also for battery energy storage, is going to be down the road. Another factor that's kind of also influencing this picture in a big way is the policy support. So there are lots of states that not only have targets around decarbonization of the power system, but they also have explicit targets regarding energy storage deployments by certain timeframes. So this creates effectively a great market pull for both existing technologies, but also new technologies such as the ones you've heard before. So one of the complexities of thinking about energy storage from the grid perspective is that it does provide a wide variety of services, and however, at any one point in time, it's likely that it's providing at most one or two of these services. So how does one think about the relative value of the various services that energy storage can provide? And then secondly, as we think about energy storage, the nature of energy storage is such that it leads to increased coupling between the operations of the power system between one time period and the next. So as we sort of think about these two attributes of energy storage, and then we play out what is likely to be a future power system that is dominated by variable weather-dependent resources like wind and solar, it raises the question of how we actually go about understanding the value and the role for energy storage in these systems in conjunction with all the other technologies that are coming on board, not just energy storage, but wind and solar and maybe other dispatchable generation sources. So at the MIT Energy Initiative, as part of the Electric Power System Center, as well as other research efforts that MITei is supporting, we're looking at this question of sort of evaluating the role for energy storage. And we have sort of a two-pronged approach here to think about this. So firstly, as we move to a system that has um, increased reliance on temporally and spatially variable supply side resources such as solar and wind, it's important to characterize these resources very well, because that implicitly has an implication on the role for energy storage. So that's basically the picture on the left, where we're sort of relying on uh, publicly available data sets of resource availability, mapping them onto what are the megawatts that you can actually get at a given site, while also recognizing land limitations, so on and so forth. And then all this information then needs to be packed into systems optimization models, which essentially allow us to think about the interaction effects between various technologies. So capacity planning is a very common approach taken in the electric power system, um, to think about long-term investments in generation, transmission, and distribution. And so this tool needs to now be adapted to think about planning for a future system where you have a lot of variable renewables, but also increasingly energy storage technologies. So part of our emphasis is on sort of upgrading existing capacity planning tools to have higher resolution of hourly operations, so that we can not only capture the variability of these resources, but also the intertemporal coupling that energy storage presents itself. And then finally, because the electricity system has many different services, aside from sort of energy that's the core service, um, one has to think about sort of the role of all of these technologies in meeting those different services simultaneously. So having a configurable network and a market representation in these types of models becomes essential. So for people who have further questions, I've put in a link of the the tool and the documentation at the bottom, but the bottom right chart just gives you a sample of how this capacity planning model, which we call Gen X, is able to sort of think about the hourly dispatch of the system and use that information then to provide guidance on what would be a cost-effective investment plan, uh, for a range of emissions and technology scenarios. So the real purpose of these tools are basically to sort of be able to play out a range of what-if scenarios that can then inform both policy, but also inform and develop technical benchmarks for various uh, technologies, such as the storage technologies you heard about from the previous two speakers. So in the next few slides, I want to give you a flavor of some of the learnings from our own assessments over the past a few years with regard to energy storage, and in particular battery storage. So the first study I'll talk a little bit about was where we were trying to sort of understand the value side of the equation of energy storage in the bulk power system with increasing wind and solar penetration. So you've heard a little bit about sort of what makes up the cost of these systems in terms of as you're putting these systems in the field. We wanted to take a look at it from the value side, where energy storage could provide a range of different applications in energy networks, ancillary services, and capacity. And when you sort of account for the occurrence of those events and stack the economic value that you can get from those services, how does it compare against the costs? And for the modeling, we've basically tried to go with an relatively agnostic representation of storage, with looking at lithium-ion type round-trip efficiencies and characteristics in terms of discharge, so on and so on and so forth. So let me just walk you through some of our key findings here. So what you're seeing on this slide is a plot showing the system value as a function of a number of different system scenarios. So what we basically tried to do was we developed two abstract power systems, one that looks like New England and one that looks like Texas. And then for each of these power systems, we modeled the penetration of uh, renewables in these systems at different amounts, going from 40% of annual demand to all the way to 60% of annual demand. And then within those systems, for each of those penetration levels, we force in different amounts of energy storage into the system, ranging from no energy storage all the way to energy storage equal to 40% of peak demand. And in this case, in this particular chart, the energy storage is sized to have energy to power ratio of 4 hours, or an energy capacity equivalent to provide 4 hours of 4 hours of supply at peak power. So what you see here is that as you look at the different bars under each of the VRE labels, which corresponds to the renewable energy penetration level, what you see is that as you are adding more energy storage into the system, you're basically having a diminishing returns to scale with respect to value, which basically is not that surprising when you think about how energy storage actually operates. And a larger implication of energy storage is primarily around the fact that it is trying to smooth out fluctuations between supply and demand, and in many of those cases, having many of these units without altering any of the system conditions leads to sort of a declining marginal value. So the very first unit sees a very high value, but subsequent units might not see as much value. But at the same time, we are not living in a static system with a constant amount of renewables penetration. And so really what's interesting is how the energy storage value actually changes as you add more renewables in the system. So as you go from, say, 40% generation coming from renewables to 60% generation coming from renewables, you see a massive jump in the value of energy storage, particularly for the initial few capacities, initial few increments of energy storage that you're deploying up to 10% of peak demand. So how do we think about this value? So one way to think about this value is to compare this value which is on an annualized basis against the annualized capital costs that might be possible for these systems. So as I mentioned, this value calculation is agnostic to the capital cost, so we can overlay over these bars, estimates of what we have, what the literature suggests would be capital costs of systems for different storage technologies. So the blue line here is just a representation, for example, of one estimate for lithium-ion battery storage costs that we have seen in the literature. So this suggests that basically, for today's cost of lithium-ion systems, there is a significant cost effectiveness of deploying energy storage, up to 10% of peak demand if the systems at 60% penetration of renewables. However, if the systems at lower penetrations of renewables, then they may be lesser value and in some cases no value. As we sort of see the trajectory going forward for cost of these technologies, which is continuously a moving target, if you were to sort of think about a world where storage costs are much lower at $150 a kilowatt hour, then what we find is that there is a much greater value for energy storage across the spectrum of scenarios that we've considered here. So you see a similar trend in the case of the Texas case study. The difference between New England and Texas is largely driven by the fact that the resource makeup in New England is largely driven by wind, whereas in Texas you have sort of equally good wind and solar resources. So the consequence of that is that storage has slightly lower value when deployed at the initial levels compared to in the New England case, primarily because wind and solar, their availability partly tends to complement each other, and so that in some ways allows you to mitigate the need for storage as you sort of get to these higher penetration levels. Nonetheless, the other trends with respect to increasing storage penetration and renewables penetration are largely true here as well. And so if you start to unpack, where all of this value is coming, because of the way we've done these calculations, we can start to sort of understand, what is the source of value for these bars, and what are the various sources of value in terms of the various grid services that energy storage is providing. So this chart here basically takes each of the bars that you saw in the Texas value chart and breaks them down by the various services that energy storage is providing, ranging from network deferral, capacity deferral, whether it's in renewables, thermal capacity, as well as changes in fuel costs, which basically reflect the dispatch of the system, as well as in avoiding thermal power plant starts. So there's a lot of detail here, but the key takeaway here is that nearly all of the value in many of these instances is coming from the deferring of investments, either in the networks or in the capacity of renewables or in the capacity of thermal power plants, where you're able to prematurely retire some gas capacity or find the need that you don't actually need to add that gas capacity with the presence of storage. So this has implications as we think about how we may value energy storage in electricity systems. So in the near term, one of the clear indications from this analysis is that there's a lot of merits to think about integrated renewables plus storage projects, because those projects can truly capture the capacity deferral value that storage provides, at least with respect to renewables penetration, which is the purple bar on this chart on the left. Another important attribute for energy storage as we sort of increase decarbonization levels is to think about how it can firm up the variability in renewables, as I mentioned earlier. And so one of the metrics to think about that is to look at what fraction of energy storage capacity is available during times when the grid is the most constrained. And so these are hours which we call as net load hours, where the grid either has low renewables output or a combination of low renewables output and very high load. And so if you just focus on the capacity contribution of energy storage during those top 100 net load hours, say for an example, we can start to paint a picture of what kind of substitution energy storage can provide for natural gas generation, which would be currently deployed during those hours. So what you see here on this chart is basically that across the two systems that we analyzed and across the range of energy storage durations, we see, while you're trying to sort of provide all these other different services, it may not be possible, at least for the durations we've considered here, to be able to provide all of the storage power capacity for providing energy during these grid constrained hours. And so you might need longer durations energy storage in many of these instances, which again then comes back to what is the cost of those technologies and whether it's actually cost effective to deploy in the first place. So the key takeaway here is that as you're thinking about storage playing a role to substitute for dispatchable generation like natural gas in the longer term, it really boils down to the system dynamics in terms of the mix of renewables, but also the level of storage penetration in the system. So in the next few slides, I'm going to briefly touch upon some ongoing work that is building on this analysis of understanding the dynamics of how storage can gain value in the electric power system, to understand sort of what role storage might play now in deep decarbonization of the power system. So the results I was presenting to you so far, we're looking at sort of penetration levels anywhere between 40 to 60% of wind and solar. But truly, if you are looking to decarbonize the entire power sector, it may be necessary to go much beyond that. And so this is work which is a collaboration with several of my colleagues as part of the MITei Future of Storage study that Rob mentioned in the introduction. And so a lot of the work here is preliminary, but we have some interesting insights here that I think would be happy to talk a little bit more about in detail in the next few slides. So our approach here is pretty similar to the analysis I had shown previously, where we're sort of trying to understand, the role for storage in different US regions, but also at the national level under various emissions and technology scenarios. And again, a lot of the answers regarding what's the role for storage or what's the break-even point for storage when you see large-scale deployment, it all depends on the regional mix. And so to understand how those regional factors affect the solution, we've been looking at these two regions. The Northeast is interesting because it relies heavily on hydro resources, both in upstate New York, but also from Quebec. It has access to both onshore and offshore wind resources of relatively high quality, but at the same time, it's got relatively poor solar resource. The Texas region, as we've talked about, has very good solar and wind resources, but not much hydro resources, and it has a very different demand curve compared to the US Northeast. And so, our efforts here, and when you're thinking about deep decarbonization of the power system, have largely been trying to focus on making sure we are actually capturing really the variability of wind and solar at multiple timescales, both in the order of days, weeks, but also across years. And so we're using data sets that span 7 years of historical weather, for which we have resource information regarding wind and solar to be able, and particularly focusing in on those weeks which we call as extreme weeks with sort of relatively low wind and solar availability, to ensure that some of our insights are essentially robust to that assumption. Like with any of these modeling efforts, there are a range of different input assumptions that go in, and I'm happy to talk through many of these, but in the interest of time, I'm just going to skip that over, noting that we're trying to sort of look at a future electricity system that has significant amounts of electrification, and try and understand sort of what the implications are of various emission scenarios and technology scenarios. So the first key result I'll start with is focused on trying to look at a system where we work with the technologies we have today, which is natural gas, wind, solar, hydro, both as reservoir and run-of river and pumped hydro resources, as well as lithium-ion electrochemical as the sole electrochemical energy storage technology. And so what I'm showing you here on the two charts on the left basically show you the modeling outputs for when we enforce going from a no policy limits case all the way to an emissions intensity constraint of 0 grams of CO2 per kilowatt hour, what the overall system capacity in terms of power capacity deployments looks like for Northeastern Texas. So what you see here is that the as you sort of ramp up the emissions intensity constraint and increase the stringency of decarbonization, not surprisingly, you're adding a lot of wind and solar. You're adding and you're backing off a lot of the natural gas generation, which is which basically will not be feasible for the low emission scenarios. You're also seeing sort of significant increases in the electrochemical storage technology, lithium ion being deployed. This is noticeable both in the Northeast and the Texas regions. And as you sort of go to the very the zero carbon scenario, you're increasing the amount of storage requirements in a nonlinear manner. Although it's not easy to tell because the chart on the x-axis is not a continuous axis. It is also worth noting that under even the business as usual scenario, the cost of these technologies has come down significantly. That even in the absence of policies, we anticipate that many of these regions can get to much lower carbon emissions levels than currently in these systems. So for storage, power capacity is only one side of the equation, as we've learned from the previous two speakers. And so it's important to also think about the energy capacity of these technologies that are deployed in each of these scenarios. And so across the board, for Texas and New England, the chart on the right shows you basically the stored energy storage capacity as a function of the emissions policy cases. So one way to think about this energy storage capacity is to think about how many hours of mean load that this energy storage capacity can be supplied if it's discharging at 100% efficiency. And in both systems, despite the large difference in terms of absolute numbers, we're talking about roughly 8 hours of mean load for this kind of a system. And this is typically consistent with what we see for other studies as well with respect to lithium ion because of the relatively high energy capital cost of this technology. Now, one of the other competing factors that storage might need to contend with as we think about a deeply decarbonized future is the fact that renewables costs are continuing to decline. And so one of the strategies that could become cost effective to get to these high penetration levels is to just simply overbuild renewables capacity to be able to manage the periods of low resource output, whereby you're adding all this extra capacity that during periods of high renewables output will actually, a lot of that generation will be curtailed, but during the periods of low renewables output, you can use that extra capacity to basically still continue to meet demand in a reliable manner. So this is a phenomenon we see across a range of scenarios that uh, including the ones here, but also other sensitivities that we have looked at. And there are many ways to think about this, but the one sort of imperfect analogy here is around, thinking about how power systems are designed today, where not every generator in the power system operates at 100% capacity factor. We have different plants or different kind of cost structures that are set up to operate either as baseload or peakers. And so one can think about that analogy, although that analogy doesn't go very far when you think about the fact that there's an intermittency problem here. So it just gives you a little bit of a flavor that curtailment is indeed part of this solution as we think about operating and planning for a deep decarbonized system. So we heard a lot about from the previous two speakers about a range of inexpensive storage technologies that are on the horizon. And so one of the focuses of this study is to sort of provide a system view on where these technologies might fit in. And so just one example that I'm showing here is of a case where we looked at the potential implications for two types of long-term storage technologies. One of them we heard a lot from Fick about regarding electrochemical flow batteries. So, we've made some cost assumptions here, building on what we think the costs are today, and actually consulting with folks like FIC about what we think the cost might be down the road for some of these technologies. Another technology is around the use of hydrogen. So here the essential setup of the storage system would be that we would have an electrolyzer that would use electricity from the grid and produce hydrogen that can then be stored either in underground salt caverns, as is practiced at scale today, or in this particular case, more conservatively thinking about pressure vessel hydrogen storage. And then subsequently, we use that hydrogen in some sort of a turbine. In this case, we're thinking about a simple cycle that leads us to a relatively low round trip efficiency of about 17%. But if you were to replace that simple cycle with a combined cycle, you may see a slightly higher discharge power capital cost, but would lead to an overall round trip efficiency that's probably in the 30 to 35% range. So we want to sort of understand, notionally, what do these new technologies buy you at the system level in terms of both in terms of the deployment of capacity, but also in terms of system costs and other impacts. So here I'm showing you an example in the Northeast where we looked at three scenarios. One is a scenario with lithium ion, which I talked about previously. Then you have a scenario with flow batteries, and then a scenario with flow batteries and hydrogen. So it turns out, at least for this set of assumptions, flow batteries tend to be very competitive. And in many of these cases, they tend to sort of largely displace lithium ion in a large proportion for many of the carbon emission scenarios we're looking at. Hydrogen is less attractive in the Northeast, and part of the rationale here is that we have a lot of pumped hydro and hydro reservoir resources that do provide a significant balancing capability, and so a technology with relatively low round trip efficiency like hydrogen becomes less attractive, even though it has much lower energy capital costs. In the Texas case, in contrast, we see that hydrogen has a role to play where there is not any hydro resources to balance the system. And so as we go to sort of the lower carbon emissions cases, particularly 0 grams of CO2 per kilowatt hour, you see the purple bar here indicating both flow and hydrogen could play a significant role in these types of systems. Now, it's important to note that, as I mentioned earlier, what these long-term energy storage, long-duration energy storage technologies buy us is essentially, some displacement in renewables capacity, which then translates into reduced curtailment of renewables. So it sort of mitigates the need to overbuild renewables, which could be particularly useful if there are land restrictions or public opposition to deploying a large amount of renewables, or other factors that might impede such deployment. But also, energy storage leads to sort of larger energy storage capacity being deployed, which makes sense given the lower energy capital costs of these technologies. So across the two systems, when you think about the deployment of cheaper energy capital cost technologies, you see a lot more energy storage being deployed in many of these systems. And this is indicative. This has implications both in terms of how we think about the overall system costs of delivered electricity, which is often a metric that's used to think about the cost effectiveness of decarbonization in different policy and regulatory settings. One of the dimensions that's important to keep in mind here is that the availability of these lower energy capital cost technologies tends to reduce the overall system cost to achieve the various emissions intensity targets. And of course, this would depend on the specifics of the storage technology characteristics. So I don't want to emphasize too much about the specific differences, but notionally the idea that these lower energy capital cost technologies are important because they can actually drive significant cost reductions. That said, there is also a significant role for demand side resources to be competing in providing flexibility in these systems. And we find that, as you get to sort of the really low carbon scenarios, demand response tends to be a significantly cost-effective metric and approach to balance the variability at shorter timescales nonetheless. So I'll finish with one last sort of result. This is sort of now zooming out and trying to look at a national level, what implications energy storage has in terms of deep decarbonization, and what are the competing factors that might influence energy storage. So when you sort of think about the the national level analysis, a key competing factor with energy storage, which basically moves energy in time, is transmission, which effectively is a measure for moving energy in space. So one way to think about this is to sort of think about modeling a zero carbon power system for the continental US, where we look at balancing either over states, where if you were to do it for each and every state, then sort of the generated weighted system electricity costs can be quite high, because not all states have these good quality wind and solar resources. Think New Jersey, Massachusetts, northwest part of the US. And so consequently, in that kind of a framing, you have a very large requirement for storage in the system. However, if this is not how the electricity systems operated today as well. In reality, we are sort of operating and balancing electricity over a zonal region, such as the PJM ISO or the New England ISO, or even the Western Interconnect. And so when you start balancing over larger geographical areas, you're taking advantage of the different weather patterns that exist over such a over larger geographies, and exploiting that to minimize the system costs, as well as reducing the need for storage as you go along. And then if you sort of extend this analysis all the way to going to a fully interconnected US system, then you start to see significant cost savings resulting from using the different weather patterns, but also exploiting the fact that if you are able to build transmission, which is a big if, and has been a very challenging regulatory process for deploying transmission in the US, but if you're able to overcome some of those barriers, then really you can balance energy over a much larger geography and see much greater cost savings. So I'll stop there. I know we may be sort of approaching the limit of the meeting, so I'd leave these key takeaways here, and thank you for your attention, and I'll be happy to take more questions from the audience.
Thank you very much, Derek. That was really interesting. We have again lots of really interesting questions and not a lot of minutes, so I'm going to try to compress some of these questions into maybe a synthesized question. And you made the point in many ways that the cheapest kind of storage is sometimes no storage, either by overbuilding or by expanding our transmission network to allow power to be moved from one place to another and account for excesses and needs, by perhaps better balancing demand and availability of power instantaneously through demand response type activities and so on. And one very good question here is, does this mean there's no need for long duration storage to reach full decarbonization? You did have a slide on that, slide 10, where you talk about that a little bit. Can you say more?
Yeah, so I think, that would be the wrong interpretation from this analysis. I think what we are trying to sort of play out is just understand the different levers that we have in terms of operating the power system to balance supply and demand. And I think I'll echo the sentiment of the previous speakers that you really need a combination of all of these strategies. And there is a lot of uncertainty regarding both the feasibility of, say, deploying long distance transmission, as well as the ability of demand response to show up when it's actually needed. And so sort of given those uncertainties, I think the more options we have on the table with respect to being able to think about balancing a power system that's largely reliant on wind and solar, I think the better off we are. And one other thing I'd mention about long duration energy storage is that, because of the modularity and the relatively simplistic sort of, timelines associated with constructing and deploying these technologies, they offer sort of potentially an easier to market strategy if you can, make these technologies reliable and at scale. So, and one other thing regarding energy storage is that, if you can actually make it cheap enough, there are strong indications that you can actually reduce the overall system costs with these technologies. So I think, there are significant reasons to think about new technologies in energy storage.
One aspect of the use of storage we didn't get a chance to talk about much in your presentation is the location of storage within the grid. I mean, at a technical level, how close storage is to large loads, for example, where it may be in the distribution or even the transmission system. Right. Can you talk about that effect a little bit?
Yeah, so I mean, I think that's a great point, because one of the drivers for where storage kind of operates on this arbitrage principle, and so it's similar to the real estate market in that location is everything for the energy storage. So if you're thinking about capacity deferral as being sort of a key metric, there are significant opportunities in the distribution system where, rather than upgrading a substation, you could deploy storage to sort of mitigate power flows during peak hours, and that could be a very profitable application. And then sort of the more downstream that you're closer to the consumer, you're adding the array of services that you can provide, not just to the consumers at the distribution level, but also to the bulk power system. So it does allow you sort of more flexibility in some ways to think about it. That said, small scale installations of storage have some um, economies of scale challenges. And so that is a factor to contend with as you think about deploying storage at various locations.
You talked a lot about the duration of storage as well, and showed some nice graphs where it really doesn't look very attractive to go to 40-hour storage in many situations, because the capacity factor begins to fall off rather dramatically. What's your feeling about the duration of storage that will be needed on the grid, really?
So one of the interesting things we've been trying to do is try to sort of understand. I mean, I think people think about energy storage as being either a daily cycling or a weekly cycling or a seasonal storage. And what we actually find from a lot of the analysis of looking at the hourly simulated profiles of how the storage asset operates is all storage technologies tend to have a preferred first strategy, which may be either daily, weekly, or seasonal. But nonetheless, all storage technologies do a little bit of everything. And so you find that even with a technology like hydrogen, which has very high capital costs but very low energy capital costs, it's primarily set up to do weekly or monthly or seasonal storage. But you do see from time to time, depending on the conditions on the grid, that hydrogen storage may be needed for some amount of daily cycling. And so the answer is, and in some ways a good answer, that it's a portfolio solution. There isn't really a number for energy storage duration. I think you need sort of a portfolio of storage technologies to address the various different needs. But there will be competition between these storage technologies that one has to contend with as we think about cost effectiveness.
Mm-hmm. We've come to the top of the hour and then gone a little bit beyond it, and I'm conscious of the need to end on time. So I'm afraid we have to wrap up there. It's been a really, really interesting session pulling these things together, and I know everyone would like to hear more. I see lots of questions about hydrogen brewing as well, which is a topic that perhaps we should have a future discussion on here at Zoom Towers. Dharik, I'd like to thank you for your talk, and also once again thank Don and Fikele for theirs. I can't help coming away from this session feeling optimistic that although we may not know exactly how we're going to get there, we're going to get there. I think we're going to have a combination of technologies that enable us to fill these needs on the grid. Perhaps a change in the structure of the power system that enables it. All of these things are happening, and happening very quickly, quicker than we ever thought. And so I think that we'll leave it there, and I'll return it to CJ, and hopefully everyone shares my optimism. Thank you very much.
Okay, many thanks, Rob. Also, many thanks to our speakers. It was a great session to provide deep insights from chemistry to storage system to the integration to the grid. I want to also thank our audience to stick with us for 2 hours, especially some of you from the other side of the world. I know lots of questions have not been answered because you have so many, I see so many questions, but as the speakers mentioned, you can reach them if you feel you have some really great questions to ask them. Obviously, as I said earlier, the Industrial Liaison Program and MITei Energy Initiative are aggressively working with the industry. So if you are interested in working with MITei, reach to us. You can definitely reach to me, guocj@mit.edu, and hope to see you later in this special time and beyond. That will conclude our session today. Thank you very much. Bye.